thank you all for coming. We're thrilled to be here again at the Fitzwilliam for what is the 5th annual lecture held in memory of Mrs. Gretchen Amphlet. It's her family that make it possible for this lecture to take place, and we'd like to thank them for their ongoing support. So on the panel tonight, we've obviously got, joining Mark and Matthew, I'd also like to say we've got Claire Bale from Parkinson's UK. She's Research Communications Manager and has worked for the organisation for almost 5 years. So if we can assemble at the front, those that are joining me in the panel, and do we have our first question?
Thank you very much. Two absolutely fascinating talks. And I'd just like to ask Professor Wood, if you get this treatment into a cell via your exosome, is with the RNA going to affect permanently the DNA of that cell, or is it just going to be for that cell's life?
Yeah, no, I think that's a very good question, and it's an obvious concern. In the context of the particular RNA type of treatment I was talking about, that treatment will last for a short period of time, probably days to weeks. It won't affect the DNA of the cell. It's likely at present that we would need to re-administer that type of treatment, so it wouldn't permanently alter the DNA in the cell. But there are types of treatments, certainly genetic therapies that people are developing, where they might permanently alter the DNA of the cell. But the particular type that I was talking about is something that's transient, that would last for days or perhaps as long as a month.
Hi. Is the suggestion then that perhaps the alpha-synuclein is encapsulated in these vesicles? Is that where this is tending towards? With your mice experiments, you said this was a kind of before and after. Well, it was really a control and a not control. Is the implication that we're actually reducing the size of the Lewy bodies once they have been formed, or is it just we're preventing them from forming?
So to come to the first part of your question, I think there have now been published evidence that some of these vesicles derived from dopamine neurons do contain alpha-synuclein. So I think that's the suggestion as to their possible involvement in the mechanism of transmission of the disease, that they could convey a protein like synuclein from brain cell to brain cell. So I think that's absolutely right. In our experiments, these mice were treated for a relatively short period of time, and they had already developed some degree of pathology in the brain. So what we were seeing in the images I showed you were Lewy bodies, were aggregations that had been reduced by treatment for a couple of weeks.
And was there behavioural change in the mice?
Yeah, these are experiments that we're doing at the moment. So that was a relatively short-term study. We've now embarked on much longer-term studies. So I can't really answer that question at the moment, but it's exactly what we're trying to find out. Yeah.
Fascinating.
Sounds like you need to have a conversation at the end, I think, as well. Any more questions? Okay.
I'll preface it by saying, of course, my knowledge of science and technology is Neanderthally small compared with yours. But you used a phrase, Dr. Wood, you talked about reducing the alpha-synuclein, yes, and the Lewy thingies. And you actually used the phrase switching off the alpha-synuclein. It's always, my wife has had Parkinson's for 14 years, and when she sleeps, a switch is turned off. Her body is absolutely still until the morning. Unless occasionally, if I touch her, she'll start to vibrate again, but then it sinks back down. And then in the morning, the motor turns on again. Yes? Is there any connection between the reduction that you talked about and what's going on there, or is there no connection, in which case I'll shut up and...
I think the answer is that there's probably no connection, but
Right.
I would urge you not to shut up, because I think it's a very interesting question. And Mark might like to comment on this, but I certainly know within Oxford we've recently established a sleep institute, and one of the major goals of that institute is to understand how sleep affects the development of neurological diseases and particularly psychiatric diseases, so the combination. So I think we know rather too little about this, but I think the idea that sleep becomes affected in disease, that actually modulates disease, that affects whether we get better or worse or how bad we feel is actually very, very important. So what you're observing during the sleep is probably a very important effect of the parts of the brain that are involved in sleep having an effect on the parts of the brain that are affected in Parkinson's. And Mark might like to comment on that, because he probably knows a lot more about that than I do. But I think it's a very, very interesting and important question.
Yeah, yeah. So Mark, with whom should, if we ever wanted to have another conversation, we don't even live in this country, by the way, if we ever wanted to have a conversation on this theme, might we attack you one day, or is there anybody else?
Absolutely, you should feel free. So, I mean, I would sort of broadly agree with what Matthew says in terms of sleep being, people are more interested now in sleep and how that's affected in various disorders, and also how sleep may be very important for improving or exacerbating symptoms of disorders. And also that this is clearly telling you something, and I assume actually that this is probably quite common observation that you've made, and of course that's telling us something interesting about how these different circuits are interacting, which is very interesting, I think.
Okay,
Yes.
then thank you both. Okay.
There was one towards the back in the centre I saw earlier. Yeah, still have a question. Oh, okay, sorry.
Okay.
Yeah.
Just to follow on that comment that has just been made to you, I have restless leg syndrome, and it comes on at night, not during the day, which seems the reverse of what's just been told. So I just want to throw that into the pot, if you like.
I think it's an example of just how complicated this condition is. The more people you speak to, the more variety you see in the way it manifests itself. So yes.
Preliminary question. Do you think James Parkinson knew about the blood-brain barrier when he developed levodopa?
James Parkinson?
Yeah.
Well, I'm not sure James Parkinson developed L-dopa.
No, that's in the 60s, actually, wasn't it?
So L-dopa was developed about 50 years ago, in the 1960s, late 1950s.
James Parkinson, yeah, sorry.
So, but James Parkinson probably would almost certainly not have known about the blood-brain barrier when he described the early cases of Parkinson's disease.
So when L-dopa was developed in the 60s, would it be known then?
So they would have known about the blood-brain barrier, but I don't think they developed L-dopa specifically to be effective in reaching the brain. I think they developed it specifically as a mimic, as a dopamine mimic, and I think they were probably just very, very fortunate that the structure of that drug allowed it to cross easily in the brain, into the brain. I don't know.
Yes, that's my understanding as well.
I think it was probably chance, probably good fortune.
Well, what troubles me about Parkinson's in the UK too, why are you not coordinating research better to concentrate on these vital issues?
Okay. Well, do you want to go?
Go on, Claire, please.
Oh, well, I think it's a really good question, and it's something we need to do much better. And you may know that we're coming to the end of our current research strategy, and in the new research strategy, we're very keen to do that better. We're already talking to many more biotech companies, pharma companies, and trying to bring people like Matthew together with pharma companies and talking about how we can work together better and actually unite the Parkinson's community, not just in this country, but actually all over the world. So hopefully we'll be having fruits from that in the next few years.
Thank you.
The gentleman up there described himself as a Neanderthal. My question is even more Luddite. My wife's had Parkinson's for 19 years and had subthalamic nucleus bilateral deep brain stimulation 5 years ago, which has been very effective. But when she got it, we read a lot about it, and we were told you've lost 80% of your dopamine-producing cells by the time you get a diagnosis, and you've said that again today. My general thinking about evolution and what happens in nature is it's very efficient. Trees grow sufficient roots to stand up, not to be blown over by the wind until they get caught out. Is that not the case in the brain? Why is it there's so much? Why is there an over-provision?
Great. So I think this is not well understood. Certainly it's not well understood. It may be that the symptoms at diagnosis are quite dramatic, and that there are more subtle functions that are lost, and so there's maybe not as much redundancy in the system as it seems. But yes, on the face of it, it appears that there is a large amount of redundancy, and it's not really clear why that is. I think another possibility is that this idea that there's such a large amount of degeneration before you're diagnosed, and maybe Matthew might comment on this. It's often suggested that that's the case, and I'm not sure how the evidence is. Might be more variable. It's hard to really assess that.
It's likely to be about right. I think you probably do have to lose probably 50% or more of your functional neurons to manifest symptoms. There's a wonderful book by an evolutionary biologist called Jared Diamond, who's based in California, who's written a lot about exactly this question. Why does it appear to be this apparent redundancy in all of our bodily systems, where we appear to have too much? We can do with one kidney, why have two? We could do with a liver that's 10% of the size of our liver, so why have such a big liver? It's true of almost every system you see in the body. So if you'd like to read about it, I'd encourage you to read his book. But one of the analogies he draws early on in the book is about a company that you probably all know, a company called, I think the company that we're familiar with might be Otis, a company that makes elevators. It would be absolutely catastrophic for that company if there was ever an accident involving their elevators. So they build in all sorts of excess capacity into the design of those. They could, you walk into an elevator and it says this will support 8 people, this elevator. Actually, it could probably support 60 people, because it would be such a catastrophe for that company if there were ever an accident. They wouldn't get any more business. So it's all of these fail-safe mechanisms that are probably built into our physiological systems in the body that are trying to ensure us against the risk of something catastrophic going wrong. And something catastrophic probably goes wrong in all of us ultimately at some point, but on the whole we keep going for a remarkably long time in pretty good health, most of us, and that's probably because of all of this spare capacity that's built into most of our systems.
Thank you. Related to that last point, you said if you've got 50 to 70%, say, as a threshold level before you start seeing symptoms, could it be that among the different types of connections you showed in that the dopamine neurons connecting to different parts of the brain, some are more important than others, or more susceptible than others? So you have to go through 50 to 70% before you've actually lost enough of those particular ones that are particularly important.
Yes, so that's certainly a possibility. There do appear to be subgroup. So although dopamine neurons in substantia nigra are particularly vulnerable to degeneration, even within the substantia nigra, there are particular types that appear to be particularly vulnerable. It seems to be related to whether they're expressing calcium-binding proteins. So yes, that may well be the case, that there is a subgroup within a subgroup, as it were. Yeah.
I'd just like to ask why. Why do the cells start breaking down and not working properly? What we're doing, we're finding out what we can do for it when it started, but why does it happen and how can we prevent it?
That's the ultimate question. I mean,
maybe I'll start very briefly, and then so I think that probably the view in the field is that there are multiple causes. A popular idea is that dopamine neurons and other neurons that are degenerating are undergoing multiple hits, and so they are particularly vulnerable for some reasons relating, for example, to their anatomy, to the fact that they make dopamine, to their ongoing physiology, and that all of these factors combine to lead to degeneration. And that it may be that the buildup of Lewy bodies is the first important step that then leads to degeneration. Over to you.
Yeah, no, I think, well, we don't know the answer to the question. And it's a very good question, and we don't know the answer. I think Mark's absolutely right. I mean, there are very striking similarities between a disease like cancer and a disease like Parkinson's. In cancer, you have the opposite problem. You have cells proliferating in an uncontrolled way, and in a disease like Parkinson's, you are losing cells that die in an uncontrolled way. And it's very likely that we know a huge amount about cancer, we know less about Parkinson's, but it's likely to be that there are many similarities. And the one that Mark's alluded to is that you need to have multiple defects in the cell. Many of these might be accumulated over time that ultimately predispose that cell to dying prematurely or degenerating. So it's very likely to be a complicated problem. In only a small minority of cases might it be a simple problem that could be due to one factor or one overwhelming factor, but for most cases it's likely to be due to multiple factors that develop over time and that predispose that cell to degenerating or to dying prematurely. And we're beginning to understand what some of those are. Mark alluded to one in his talk this evening, which was the energy requirements of cells like dopamine neurons that have to maintain such an extensively branched structure. So any compromise to that cell's ability to maintain energy within it is going to be one of those many factors that could be amongst the long list of factors that will predispose that cell to dying early.
Thank you. I'm an ordinary person with Parkinson's, having been diagnosed coming up for 8 years ago. I was buoyed up and given confidence to ask a question by the mention of thingies from the back, because that's my level of understanding. The other end of the last question is how long now do we need to give it till we find something that will stop us carrying on? I don't want to be able to say I've had Parkinson's for 40 years. I want something to happen sooner. So the question always on my mind is how long?
Who wants to have a go at this one? Anybody? Claire?
Well, I think that's the hardest question there is to answer, and I don't think anybody could give you an honest answer that wasn't a guess, really. We want it, and ultimately, the more work we can do, the faster we can do it, the more money we can invest, the more people we can get together working on these problems, the faster we'll get there. So it's not how long is a piece of string, it's like how many people can we get working on that piece of string to get the answer. But I really shy away from giving a 5, 10, 15, 20 years, because the answer is we just don't know. If anyone else wants to be braver and hazard a guess.
Just to add to that, I think it's interesting. I was chatting to Matthew before this lecture started, and he's already alluded to the point that cancer's had a lot more money spent on it than obviously Parkinson's has in terms of its research. And I did ask Matthew with his own project, what would it take to take that learning through to treatment? And what was your answer, Matthew?
Somewhere between £5 and £10 million.
Yeah, so clearly there is a need for more investment, and that will speed things up. I think that's just a truism at the end of the day. But in some of the cases, to actually deliver potentially quite beneficial things, we're not talking about sums of money which are just out of order. I think we should have some hope, but I don't think we can put a time scale on exactly when the next levodopa is going to come through, which was the really big breakthrough, I suppose, in the last 50 years. So, anyway, we can take one more question. Yeah.
You talked about, Professor, the fail-safe mechanisms that we have in our bodies. Presumably, that is what the blood-brain barrier is for, to protect us. is there a danger by going through that barrier and bursting through it that we might open up another catastrophe?
Yes, well, no, that is a very, very good question. The blood-brain barrier, I mean, it's there for a purpose, and we believe that purpose is to control what goes in and out of the brain, to expose the brain to what it needs, but to keep it free from things that could cause damage. And the brain, you know, as you would have appreciated from Mark's talk, is a very complex structure, and it requires a very tightly regulated local environment in which all those nerve cells can work. So that's why the barrier really has evolved and why it's there. It's interestingly, not all of the brain has a blood-brain barrier. I didn't have time to go into all the details, but there's a small part of the brain that actually doesn't have a blood-brain barrier, so that's quite interesting as well. But you make a very, very good point. And there are cruder methods that people have used for some time to try and open up the blood-brain barrier. And that's certainly not what we've been developing or proposing, but I think people are aware that there are dangers associated with opening the barrier and making the brain readily accessible to everything that flows in the bloodstream. So certainly what we're trying to do, and I think what people now believe is necessary, is a very intelligent type of technology, if you like, that can actually take advantage of the normal transport systems that the blood-brain barrier has, rather than crudely opening it up and therefore exposing the brain to potential damage. So we hope that's not one of the consequences of what we're doing. We certainly believe that it shouldn't be, but you're very, very right to raise that problem, and it's something we think about a lot. But we hope by harnessing a natural mechanism as we are, that we will be able to avoid those sorts of things happening.
Okay, firstly, thank you very much for some very insightful questions. We always get good questions at these lectures, and it just proves you don't just listen, but you also understand a lot more, certainly than I do in some cases. So thank you for that. One thing I didn't mention when concluding after the two speakers was that, and it was something that Matthew actually mentioned, which was about researchers getting behind initiatives like Compact, which is really sort of starting to cross that divide between research and biotech, and that's come out in some of the questions tonight as well. It's certainly true that research networks and approaches to research generally are changing around the globe. They're evolving, and in many ways we need to be very proud of the fact that here in the UK it remains an incredibly good place for us to take a leadership position, which is what we want to take and are taking to a large degree at Parkinson's UK in this field. As an advertisement for the UK, if you like, I mean, just to summarise, we've got a good legal framework which allows cutting-edge research to take place, which doesn't sometimes happen elsewhere. We've got academic and commercial structures, the NHS, bless them with the healthcare system we have, the patient database that it brings, and of course, having us as a charity, which we are the largest membership charity for Parkinson's in the world, and of course all the very fact that we've got the members and the influence that they can bring to bear puts us in a good place to make things happen. What I would say is you've heard tonight that there's much we know, and probably even more we don't know, unfortunately, at the moment about Parkinson's, and particularly those precious nerve cells that we want to protect. However, what I would really hope and urge you to take away, that there is a sense of optimism, and it's not false hope. But, as I mentioned myself, in order to make the most of it, we do need to attract more investment into this area. We spend a lot, other people spend money around the world as well, but it's not enough. It's not going to give us that breakthrough in the time frame that we really want unless we do spend more. And to that end, one of the things that we're trying to do and will increasingly look towards in the future is to try and leverage funds from other organisations, seed funding, for example, and building stronger international research networks than we've already got. I think this is a way forward for us to take that leadership in research that we want to do. We want to continue to keep crossing that divide that we've talked about tonight. The pharmaceutical industry we touched on perhaps aren't playing a full part. We want to build bridges with them. There's R&D, biotech companies, all of that, which we need to work more closely with. So it just leaves me to thank you, the audience, for coming tonight. Fitzwilliam College, especially for hosting us again in the 5th year, and the Amphlet family, who I mentioned at the beginning, once again for making it possible. If you've been inspired at all by this and the research taking place, there are ways to get involved, and I do mention it each time, and I just very briefly do it again. You can join our research support network. Leaflets are available in the foyer when you leave. We're looking for people who are basically not research specialists. We're looking for lay researchers to work alongside professionals to basically vet the applications that we get for research and give us a guide as to what we should be investing our money in, things that will make a difference to the people in this room, and quickly. Equally, come along to research focus lectures. We're planning another one of these type of events in London in the autumn. It'd be great to see people there, and I know a lot of you have come a long way to this one, so bear that one in mind. And as I mentioned, finally, we have 90 plus research studies taking place. All the details can be found on the website. Do have a look. And for all these things and more, there's leaflets called Help Us Find a Cure, and they'll give you a clue as to the best way to get involved directly in the research that we're undertaking. So, finally, the lecture has been filmed, so if you know of anybody who wanted to come tonight who couldn't, or who may be interested in the speakers that we've heard from, then direct them to the website. Likewise for last year's lecture, that's also on there. This one will be put on in a few weeks' time anyway. So thank you again to our speakers. Thank you all. Have a safe journey, and we'll hopefully see you again next year. Thank you.